All right, guys. Let me share the screen here. All right, so I'm sharing. Okay. All right, I think I've graded most of your exams, so you check those if you have any issues. And I'm still finishing up that last homework. So the plan for today is we're going to do the presentations during the second half, right? They don't have to be very lengthy, just, show what you did, right? And then you need to submit a report, etc. So that will be the plan for the second half. For the first half of today, we're going to go over kind of the last big topic that we're going to cover this semester, which is actually a topic that covers a lot of things, right? So, it's kind of nice, which is stable diffusion. We've already started this discussion last week with what? Images and convolutions, right? So you guys saw that. So today I'm going to give you the code basically for stable diffusion. Again, the same idea as the LLM code. The purpose of this class is to train these things from scratch. All right, so no transfer learning. Obviously that would be a better approach, but we just want to learn what we can do with pre-training models and also understanding the architecture of our model really well. Plus, there's a lot of concepts there of how embeddings work and lots of things. So I like the approach of taking a big model and then just working on it because there's a lot of moving parts in there that cover other topics. Okay. So obviously these are the big models I showed you last week. What you could do with stable diffusion models, you can write a cat on a tree in space and a meteor is behind it or something, and then it renders that image, right? So obviously that's what you get when you've spent a lot of money and things like that on developing something like that. Today, we're going to start from scratch. So our goal will be the MNIST data set, all right? But this will be your term project. This one you can do in groups of 3, okay? So this will be your term project that you have to present at the end of the semester. Are there any questions about that? So this is your last assignment, if you will. I mean, we're basically 3 weeks away from presentations at this point. So I wanted to cover this lecture today, okay? So I'm going to give you the code for it. Make sure it runs, right? And then you can start playing with it. And then over the next 3 weeks, we're going to drill down into the various parts of it as this is a big topic, okay? And we'll cover other things as well, but this is your big overall overarching model. Got it? All right, so I'll create the links for this after class today, but it's already on the GitHub. You can get it from there, and it's an example using M. So how is this going to be different for you guys? Well, it's a term project, so obviously you'll have to use images, and you can pick whatever images you want. Okay, so you'll have to look, but the example I'll provide today uses the MNIST data set, which is the handwritten digits 735. It's a type of a conditional model, obviously. So you'll be able to say, I want an 8, and it's going to generate an 8. I want a 3, and it's going to generate a 3. That's the very basic functionality of it. But what can you do with that? You can, train it with other images, right? How many images? It's up to you. How do you get the images? It's up to you. Should you use a GPU? You will need the GPU. Okay, so you won't be able to do this without the GPU. So today I'll have to demo this on the GPU. So if you're on the GPU, please just let me get one so I can demo it and make sure it runs. And then you guys can go ahead and work on it. Things that you can do with this. Well, you can encode a number and generate an image of a number, but you might be training this on cars, I don't know, or landscapes, right? Things like that. And you can, in theory, instead of giving it a number, write some text, embed that, and give it to the model. You see that? So is it going to work as well as Stable Diffusion by Stability AI or those companies? I don't know, right? But that's up to you to to make the best model that you can. Does that make sense? All right, so that will be the term project. Are there any questions? All right, so groups of 3. I'll write down the rules. You have to use the PyTorch code I provide. You'll train it with your own images. This is a conditional example that I'm giving you, but you can extend this to have embeddings from text. That's at least a keyword, right? So you could say like cat, bird, at least that. And so I leave it to your own creativity to do something like that. And you have about 3 weeks, which is plenty of time. Yes, you have to, this is literally your term project, right? So the same rules as other term projects, you present the week before finals, basically. So we have a final. Pardon? The 2nd of December? It might be, yeah. Whenever finals are that week, so it's going to be the Monday before. We'll do the presentations. Okay? And remember, that's, in the syllabus, your term project. It's a much bigger thing, right? Because here I expect you guys to get into the code, change the embedding approach, etc. And this is a big topic, but we're going to spend, lecture today, the first half, and next week going some of the ideas. We've actually already started it because we started looking at the convolution operation last week, right? So you have a sense for that. Do you have a question?
So we're going to use your code.
Yeah. Yes. That's right. Yeah, exactly. So the whole point, and play with it, have fun with it. That's the idea, right? So you're building literally, again, the same idea. It's like a competition. Whoever builds the best one gets a trophy, right? So the one that's most impressive, if you give it a poem and it renders something really nice, you might, we're doing qualitative analysis here, not really quantitative, but still. So that's the plan. Okay. All right. So I'm not hearing any questions. So I'm going to start going over the code. I need to grab a GPU for this one. The code is, I'll provide the link a little later, but it's in the GitHub already. And so this is what I'm going to do today. Just go over the code. So you guys are seeing it. Yeah. So latent diffusion. Okay. So that I've created a repo just for it. And so you can click on it and it's under stable diffusion. There are several diffusion models. This is the classic latent diffusion, stable diffusion model. That's pretty impressive. This is open source, by the way, available like the train model even. You can use it for your own company, right? So it's not a bad idea to understand how this works and then scale up. All right. So this is the script, the Jupyter actually. Okay, you can see that here. So I will go over this one. We're gonna run it in the in our environment. I'll kind of go over the parts briefly, but at the end of the training, basically we should have a model. You can see it's trying to generate. This is a generative model, right? So it's trying to generate images. So you can see here it's not very good. And as the process continues in the training, you can see the images are getting a little bit better. And then after a while, we can actually give it conditions. So you can see here, digit 9, right? So that's the input to the model. You want to generate a 9. And if you notice, all the rendered images are 9s, okay? So, if you give it a 1, then all the rendered images are 1s. Okay, so these are generative models. So I would say, large language models like GPT, which is actually your homework. You're all creating a vet GPT for today's presentation. And now there's these generative models for images. Traditional ones are conditional GANs, the generative adversarial networks. But these stable diffusion models have actually won that competition. So they seem to be better than conditional GANs. You can do this with a conditional GAN for MNIST, but obviously stable diffusion models just have more power to do things. So we'll go over some of the ideas, not today necessarily, but over the next 3 weeks, and just drill down on the different things. And like I said, what you would want to do, for instance, for your project is change this input, right? And I don't mean just change that. I mean, you have to go into how that is converted to embeddings. You know, we'll talk about embeddings as one of the topics that I still want to cover. And so you could potentially give it text. You know, there's a trick, a model called clip, and it's just made to take some text and it just provides embeddings. So you don't even have to create that whole process, right? You can add that in as like a Lego that you just add on to it. Do you have a question? No. Yeah, but that's the idea. So we'll talk about these things a little bit more. Today, my goal is just to run through the code and I'll cover some of the ideas of what's going on with stable diffusion models. And then, yeah, that would be it. But this is your final term project for the course. Any questions? So what we have left is basically this term project and then the final exam. Okay, those are the last things. I don't plan on giving you another homework. Instead, I want you to focus on doing a really good job with this one. Okay, got it? All right. So let me go ahead. So for this, it's not going to run without a GPU. So I'm going to go ahead and grab a GPU. And please, if you're all logged in right now because you're working on your homework, please log out so I can get one of these. Because I tried this afternoon, I was not able to. You should all know by now. You can grab that link. Okay, and then I'll grab a Jupyter notebook. Grab... Again, if you guys are logged in, please log out so I can do the demo. Okay. Again, guys, if you guys are logged in, I ask you to log out, right? If I can get one of these. I guess I'll have to start another one just in case with the CPU. All right, so I'm gonna select Scholar. All right, so I got this one with just a CPU. All right, so we'll start a little bit of this. All right, so yeah, okay, so this is the code as I said. I already have it on my environment, but it's gonna be the latent diffusion. So I'm gonna create an environment here. Okay. All right, so I'm going to rename this in class. And hopefully I can do a lot of this with the CPU. And when I need the GPU, hopefully I'll have it. So in class, stable diffusion. So this is without a doubt a complicated algorithm. So as you probably know, LLMs, right, GPTs, and then stable diffusions are the most complicated neural networks. So don't worry if you have to understand like a little part and then another little part and then another little part. But the code works for the most, it should work. So, all right, so I've created this. Okay, so this is the code. The first thing I'm going to do is we're going to load the data set. It's going to be MNIST in this case. Keep in mind, you guys will have this part, you'll have to solve on your own on how to load your data right into the neural network. So at some point, I'll show you an example of how I like to load data from folders, but that's something you have to solve for the term project, okay? So let's start with you'll be using torch vision. Remember, I think I said this last week. As we're processing images, we have to learn how to deal with images, and torch vision is a very nice library for that. All right, so I'm gonna put that in. So that's torch vision. That. Okay, so that's available. Okay. We're gonna, again, you saw this last week. This is a transform. It's a very nice, handy thing that basically you load your data, however you load it into your code, and then you basically can run all the data through this transform object, and it'll convert things to PyTorch tensors. It'll normalize things appropriately, etc. All right, so I create this object, transform. Then I'm going to load the data set. Notice I'm using the exact same approach I used last week of loading the MNIST data set, using torch vision data sets, MNIST, train true, transform, which is this transform. And we basically download it, and then we take the data set and convert it into a data loader. All right. We set the parameter batch size to 64, and then we indicate that we want to shuffle the data. So the exact same approach. This one you do, but you'll have to load the data for your term project from some folder, I assume, right? So you'll have to download images. You have to think about that, okay? How you're going to approach it. And, I would recommend that you start thinking about the project, like what kind of images you want to generate, but talk to me about it, like what idea you have before you start working on it. So maybe some people want to generate, as I said, cars, fashion, right? It could be that you want to generate landscapes, you want to generate things related to healthcare. Those are great ideas, but just talk to me a little bit about it. All right, so here I've loaded the MNIST data set. Okay. So now this code here just display. Oh, so this one is going to take the images. So I'm just going to grab like a little batch of images from the data set with the labels, and then I'm going to convert them to NumPy. Okay. And then I'm going to display them basically. Right? And these are basically your images. So we're going to train the model, the neural network here with these images. And as I said, the goal is you give it a 5 and it generates a 5 from the distribution. You give it a 1, it generates a 1, and so on, right? And so those things you'll have to change to say, okay, generate a happy face, an angry face, or something like that. All right, so now that we're here, so that's basically just loading the data. We need to make sure that we have all the libraries here. see them. Okay. So that's the libraries are there. All right, and now I'm going to start talking about this idea of diffusion. So the idea of diffusion is very interesting, okay? So it's almost like, I don't know, some very interesting idea. You have an image, and basically you're adding noise to that image. And you do that over like 1,000 steps, to the point where you start with an image, and after 1,000 steps of adding noise, you end up with a totally noise image with nothing. So you start maybe with, a background, right? A mountain or whatever it is. You start adding noise. That's the forward pass, and you convert the image in just an image with complete noise. And then there's the reverse step where you take that noise image and you try to obtain the original image. You see that? And that's the process of diffusion. And that apparently is the magic that makes you create these amazing images, because it used to be that in GANs, you would give it just noise and then force the neural network to kind of create images. And it works sometimes, right? It works for some problems. But this is a better approach, right? And the key thing is, as I said, you start in the training with these images, normal images, you start adding noise to them, but in steps, like, first step, a little noise, next step, a little noise, and you keep doing that until after about 1,000. And these parameters have changed. I believe the first paper was 1,000 steps, and this is probably less now, right? But it arrives at a noise image, and then once you have a noise image, obviously, you reverse back into the original image, and then you start adding the embedding part, the conditional part. And so now you're able to generate from random noise with some inputs the image that you want, and the quality is much better, okay? That essentially is the idea of the diffusion process. Do you guys see that? But initially, you can do that with equations and everything. You can add the noise as in this example, but eventually it's probably better to have a neural network just learn how to do it. So the neural network actually can learn how to do it, can learn how to reverse it, and also can learn how to score like the noise level in an image. So it's very precise, okay? So we're going to go over a blog post I have of this. And so we can see some of the main parts of it. So I never got the GPU. All right, so let's look at this idea of diffusion here. Then we can run the process. All right, so so I'm going to basically start with a simple example. Another thing is that if you have the image, right, you don't actually put the noise in the image, but first you take the image and convert it into what is called a latent image. So it's going to be, imagine that you take the 512 by 512 image of you or something, and you just convert that into a 64 by 64 latent image. Okay, so it's just going to be almost like an embedding, a representation of the original image, and then you do all the processing in that latent image. So there's, as you can see, several processes going on there, and then in the latent image, you do the noising and denoising. Okay, so I'm going to do this example here. This will take a little bit of time, but hopefully it'll illustrate it in a very simple way, the process of adding the noise and the process of reversing. All right, so you can see here we have this. This is only for illustration purposes, by the way. It's like a simulation. So this is the forward diffusion process, this function. All right, so I'm going to copy this one. Oh, I already did. Okay. And then I'm going to copy this part here. Okay. And we're going to do this part. And this will be the forward noising process. All right. So in this case, let's take a look. So we're going to have number of diffusion steps. So you guys can see that, right? So you have number of diffusion steps is going to be about 100. The original paper, I believe, was 1,000. The initial time, so this is a time sequence problem, right? So time 0, time 1, time 2, time 3. Okay. Then you're going to have a time step that you can decide what it is. So in this case, it's 0.1. So basically, we're going to increment from time 0 by 0.1. So we should get to like 10 maybe, right? Okay. Then we have an initial sample value. So you can think of this oh, sorry, I missed one. So then we have the noise strength function. So this basically just means how much noise we are adding. So in this case, it's just for this example, it's just a constant. But obviously, this is something that could be learned by a neural network. If you think about it, if it's just a regression that predicts a 1, that could predict a 0.5, a 0.7, depending on many things like in time, right? The time step that has happened. All right. And then we have an init value, which this init value you can think of as the pixel value that you're trying to noise. But remember, we're not actually noising the actual image pixels. We're noising the latent representation of them. And then this is just a number of tries just to kind of illustrate the fact that this is sort of random. Okay. So first I'll just add these functions. Okay. So these are just the parameters. Here we can set the plot that we're going to do. We're going to do 5 trials. And then basically the main idea is this. This is to simulate the forward diffusion. All right. So what that means is we have an initial value and we're going to start adding noise to it over time. Okay. So you can see this here. So we have X and T, which is the value and the time step. And then we have the forward diffusion 1D function, right, which takes in all these parameters. Once we have the point in time and the X value, we can just go ahead and plot it in our chart. Okay, so that's the basic idea. And then afterwards, we can just plot the whole thing. Okay, guys, so that's basically what's happening here. So now we need to look at forward diffusion 1D, right? So what is happening in forward diffusion 1D? And you will see that it's nothing more than just adding noise to the variable, but this is dependent on time. So here, this noise strength, if you notice, for the sake of simplicity, in this example, is just a constant. Okay, so it's just 1. And it's like the strength of how much noise you're providing to the model. So very simple. This is where it might get a little bit complicated, but it's actually just a simple equation taking X equal X plus the noise. Okay, so we're going to take a look at that. So you can see here the parameters are the initial sample value, scalar, the noise strength function, which is a function of time, and it outputs scalar noise strength. We have T0, which is the initial time. We have the number of diffusion steps that you want to take, and you have the time step size, right? And what this returns is basically the trajectory of sample values over time and the corresponding time step. So this is kind of interesting because when you create an image, right, and you have 1,000 steps of noising and denoising, a neural network could, for instance, learn, okay, I don't actually have to noise everything from 1 to 1,000. I can actually say, I just want to know, okay, I have this image. What would it look like if I added noise and we are on time step 332? Do you see that? So you can just train a neural network for that particular case. And that is very, very much something you can do. All right, so we're going to see here, we initialize the trajectory. This is going to be about 100 steps. So this should be 100 steps. So this is easy to see. I'm just going to go over here. Okay, so I have to initialize steps. Let me do that. Okay, so obviously the graph will look like this, right? Which is if you notice, we start at what? 0. It's like that's the value of the pixel, but as we start noising it, it's going to end up kind of not 0, right? It's going to end up a value with noise, basically. The reverse process is to start here and kind of end up here at 0. Do you see that? And so that's where the name comes from with diffusion. And like I said, the idea is you're training a neural network, giving it images that are normal, converting them into latent images, noising them until they're pure noise, reversing that, getting the original image, but you want the neural network then, given noise, to generate images. And then you start adding the conditions through the embeddings. So here we can see with n step is nothing more than just 100 values. Okay, n zeros is what we created here. All right, then we're going to have our initial value, x0, which is just the first value in the sequence, just gets assigned basically. And then here we generate the time points for the trajectory. So because the time step is 0.01, and I think it's 100 steps, so it should go up to 10, right? So it should be something like this, like that. You can see that goes up to 10, and that's basically our scale over here in the x-axis. You can see it goes from 0 to 10, basically. Okay? All right, so now, so we are here. Which I just did NPA range 0. All right, so I've done this step. Now we are ready to perform the process, the diffusion process, okay? This is called the Euler-Maruyama time steps for diffusion. So it's some algorithm, okay? But this is the initial idea. All right, so we have for I in range n steps, okay? And we're going to take, if you notice, we're going to need a parameter called the noise strength, which is this one, which if you notice, given time t, it predicts the noise strength, which is a function, but our noise strength here, although it receives t, it's not using it, okay? Just to keep things simple, it just returns a 1. Obviously, the actual diffusion model will be a little bit more complex and dependent on time, okay? But this is the idea of the algorithm. So this will just return a 1, so the noise strength, okay? And then we also need to generate a random normal variable, random normal. And then you can see this is what's going on. So this is you update the trajectory using this approach. And basically all it means is you take the original x, right, of the trajectory, imagine the pixel value, that selected pixel value, and the next pixel value is going to be equal to it plus this term. And this term is just the noise strength times a random value. Effectively, you're just adding noise, okay? As you can see, it's not more than that. And this is just captured in x variable, which is initialized to all zeros. So once that completes, right, I just did this 5 tries, right? So repeat that process 5 tries, and you can see, imagine the point, and it became just added noise. That's the idea, okay? That's the general idea of the forward diffusion process. So I'm going to change this a little bit to be number of tries to just 1. So you can see the effect. You can see it's just one trajectory, okay, of x. And notice it is random, right? So there is random with a certain degree of strength. You will want a neural network to learn these things, right? And which neural networks can do, right? So this is the thing that we know about, but we need it to be dependent on time. All right, I'll do 3 just to kind of illustrate, number of tries equal 3. There you go. So 3 trajectories I can do, and finally I'll do 10, kind of drive the point. So as you can see, that amazingly is the process. Now, let's go actually to GANs, right? So GANs, generative adversarial networks. The GAN was invented in 2014. This is a more recent thing. So GANs were invented by, forget his name. But anyway, in 2014, the paper came out. They're very interesting. You basically had a model that created images, right? But you have to give it an input, right? What do we know about neural networks? Neural networks, you define the input layer, and then you have all the hidden layers, and then the output layer, right? So your experience is, what are common input layers for neural networks? What are common input layers for neural networks? Just what are the standard ones? The input to the LLM was what? So, the X, right? The text, right? The text. And that became what? N by 40 by 512, right? But that was some data, is where I'm going with this, right? In your homework assignment, what were the inputs to your models, your 3 models? The CSV, which was what? Malware data, network data, phishing data, right? And what did you do? You did some classification. Okay. And what we did last week, we did MNIST just like this one. What was the input? An image. I think it was 28 by 28. It can be made into 784. It's always some input. Okay. But what, and you're trying to classify or trying to do a regression, right? But when you're doing a model, or you give it some text and it gives you some text, right? Because it's predicting the next word, right? So you have to say at least the, right? To get something, or say start of sentence and start generating some text. But in an image, what do you give it to generate an image? Think about that intuitively, right? What do you give a model that's going to give you an image? Of what? So you give it an image to get an image? A matrix of what? Okay, so you want that, and you give it that, you're saying, but what exactly do you give it? You see what I'm saying? A neural network requires inputs, right? A neural network requires inputs. I just, but I want images. So what do you give it? You give it a grid, you give it RGB. Great, that's a tensor, right? But what's inside? What are the values actually that you need to give it to generate images? Which numbers? But of what? But so then you already have the image. Do you see what I'm saying? So actually, as it turns out, when GANs were designed, they had probably that same question, and they just concluded, let's not even, it's complicated, right? So let's just not even do that. Let's just give it a grid, but with random data in it. So when you give a grid with random data in it, what is that equivalent to essentially? A noise image, right? Random data. You guys remember those old TVs, right? At 11 o'clock or 12 o'clock, it was just like snow. And remember that, right? So yeah, you just give it that. And so that's what GANs were. And so noise actually is the input to GANs, right? And so now stable diffusion models have that similar idea. You start from this noise to produce an actual image, but this approach of the diffusion actually seems to be way better. Okay, so obviously I wanted to start with this. We'll continue to drill down on this idea further, but this is a simple example of how it works, right? So basically think of it as we're just looking at one pixel and we're noising it. But noise, now it's important. With GANs, we just started with noise. We're just like 28 by 28, put some noise in there, that's it. Here it's different because the training model has actual images. They get noised over 1,000 steps in the original paper. And then once you have that noise image, you reverse the process to the original one. And somehow the neural network needs to learn that, okay? That's the trick. And, so you start with noise to produce this high quality set of images. You saw one thing that amazed me in those diffusion models is, how does it, like, I was wearing a jacket, right? And it put me in some other context, but the jacket was like made part of it, like very nicely. All right. And so I believe, this is the power of the diffusion process. Okay. All right. So I have done the diffusion part. Now let's look at the reverse diffusion. Okay. And so obviously the reverse diffusion would be, we're here and we need to kind of arrive back at the value of 0, right? So that's the process. So we're just going to look at, again, a simple simulation of this. And then, of course, stable diffusion has the actual process. Let's go here. I still didn't get a GPU for this. Okay. All right, so the next step is the reverse function over here. So I'm going to grab this function. It's similar. Okay, so I'll just say reverse. All right, so this is the reverse function, reverse diffusion 1D. Now, notice there is an additional thing in the reverse process called the score. This is just a very simplistic way, but there's gonna be, the neural network will have to give a score basically that needs to be used in the process. Okay, so we'll talk a little bit about it in the notes. So this has an additional part. And then this is just a simulation, basically. So let me grab this. And then we're going to drill down into it again. Okay, but as you can see, this is the graph that we should get. All right, so let's just run it to make sure it runs. All right, so as you can see, this is the process now. It should start from randomness, and the model needs to reduce it to the actual value, which was around 0. Okay, so there's the diffusion part goes forward and then backward, okay, in this process. All right, so again, for this example, the number of reverse diffusion steps is 100. The initial time is 0. The time step needs to be consistent, the same number of steps, 0.1. You're going to have a noise strength constant, which is defining that noise strength that we saw before. And then we have the score function for reverse diffusion. So this is just going to be that score simple function over here. Okay. The initial sample value. Okay. The number of tries. And then we're just going to loop just like we did before. Okay. So this is the 5 tries. Okay, so here we're just going to have some noise. We're going to start at noise. And then we're going to pass that noise here with the noise strength to the reverse diffusion function, which once again will print out the x and t that will be plotted. All right, so it's the same idea, but now in reverse. So reverse diffusion is over here. Okay, so we have an initial sample, the noise strength, the number of steps, and it should return the trajectory of sample values being denoised, basically, okay? So again, the same thing, we initialize the X, we give it an initial state, we do the time sequence that we had done before, and now we're just going to start at 1,000, if you will, and work our way back, okay? And so the key thing is this formula, okay? And the formula is a bit more complex than this, but it's similar to this idea, okay? In simple terms, we update the trajectory using the reverse Euler Maruyama method. And if you notice, same idea as before, we take X, right? And we're going to use that as input to calculate the next X, okay? But there's a simple formula that says that we look at the noise strength times some randomness given, which is dependent on the time step, and a score that is learned, okay? So this is just a simple example here. And then these parameters are, the neural network needs to calculate them. But for now, this is the intuition, basically. We have the previous X, and we have a formula dependent on time and a score that is going to calculate the parameter of the noise. Do you see what I'm saying? So it's like we have a little bit noise. The next value in the next step, how do you denoise it to be better? And the advantage of this is that, a neural network has weights, right? So think of it this way, right? So think of it like this. You have an image, you noise it, then you denoise it. Great. But you have some kind of an annotated data set, right? So then you take the image. This is, let's say, this part of let's just focus on this score. This is the neural network. You're training the weights of that function, right? So it predicts some value for it. The intuition is what? It's denoising it. So you're coming back, it denoised it a little, and then when you get to the end, the image that you get, is it something that is good or not? If it's bad, what do? You give that feedback to the neural network, right? And so the weights of this are going to be updated so that the next time, what does it do? It's going to take the noised image plus this component, right? This component here, where this part is weights of a neural network. So it needs to learn to produce a better score, to produce a better denoising parameter that eventually gives you the image that you want. Do you guys understand? So it's like you're setting up this idea. Take the images or the latent representation of them, add noise to them, they get to the end, then denoise them, but the neural network actually needs to calculate these values really well. So that in the end, not only do you get an image that doesn't have noise, but also the image that you want, okay? And so that's basically the process here. The neural network, it's not based on, we don't even have to, understand these equations, you know what I mean? These are just for the simulation itself. Instead, we want to rely on understand the concept of the neural network calculating these parameters by learning the appropriate weights. But the framework is really interesting, all right, of just adding and removing noise. Any questions, guys? So this is how it works. Yeah, go ahead. Because that's actually a good question, right? Because what we care about, okay, let me ask you this. What do you care about? We're trying to generate, that's actually a really good question. So do we care about creating a process that adds noise to images? Is that our goal? Is that your goal? What is your goal, actually? To obtain an image, right? We're building a generative model, right? And so we want images. And where do the images come from? The noise. Do you see that? GANs, as I said before, you literally would just give it a grid of 28 by 28 of pure noise and hope that it would learn how to generate an image. Here we have a much more powerful instrument because you take an image, noise it, and then reverse the process to the original one. And the neural network has to learn how to do that step by step. But we don't actually care about the first part. We only care about the reverse part. But because it's a neural network, we can just grab it out, right? You know, it's like, think of it as a machine that goes like this and then comes back. We can really like grab this bottom part, throw it out, and we still have something very useful. We start at noise, but we know how to reconstruct images in the way that we want it. Did I answer your question? I mean, it might be difficult, right? But to understand that from randomness, we are getting things, but this is how it works. In generative models here, especially in images, we're getting things from just randomness. And like I said, GANs were just randomness. And then you got an image, hopefully. This is a better process because you start at the image, take it to the noise, and then reverse the process back. So it's just more powerful. How they came up with that, I don't know. But it comes back from this idea of going from noise to from what is it, entropy to non-entropy, right? So to obtain the actual something that has meaning in it. Okay. All right. So I still don't have the GPU. It's I'll just go over the script kind of to give you an idea. This is something that we're going to cover, like I said, over several days. So it's not just going to be today because it's too big. There's too many things. This uses a UNet architecture. This uses convolutions, which we've already talked about. You can add embeddings to it. There's the loss function. So there's a lot of pieces. All right. So I just wanted today to cover these two graphs to give you the basic idea, right? And I'm going to give you the blog post that I have that we can start reading through, okay, of how this works. So I'll kind of just summarize now that I've given you an introduction, okay? So this is your term project again, right? This example that I provided here uses the MNIST data set. And you tell it a 7, and it's going to give you a 7. You tell it a 3, it's going to give you a 3. Because this is your term project, right, it needs to be a little bit more difficult than everything that we've done before. This is a little bit more challenging. Okay, you need to but you can work in groups of 3. You can collect your image data, whatever you want it to be. Keep in mind that MNIST used about 60,000 images. All right, so find a data set probably. Okay, I'm not asking you guys to go and collect manually like you did in the previous example, but you will need a data set of images. Does that make sense? All right, in the next class, I'll show you how to read images into a neural network. Okay, like if you have a folder, how do you read them in? So that's something that we'll cover next week. But anyway, you'll take this code, train it on your set of images, and it needs to be conditional, right? So at least you give it a label like cat and it gives you a cat. Dog, it gives you a dog or something that resembles that, right? You may not be able to get such precision. Okay? So that's the basic idea. So you'll do this project. So basically the way that it works is, and you'll have to make that change. So I'll repeat, we're using PyTorch, just like before, Torch Vision, can do transforms. This part will need to change, but eventually you're just going to create a data loader, right? So that's at least that it needs to have the format of a data loader, okay? You'll load your own images here, okay? These are just the images that we've used. The libraries, this is just the example that I did on how the diffusion process works. As I said, you noise and then denoise, okay? And the hope is that the neural network is learning some intricacies about not just denoising randomly, but denoising with some purpose, okay? To arrive at specific images. Think of it as somehow, just intuitively, you got some noise, but you got this function that does a thing, and then it does a thing, and it does a thing. And as it's doing that, I would say the best analogy is like when you're learning how to draw. Do you guys have, I don't know if any of you have, I mean, we've all drawn, right? And what did we learn about drawing? You don't usually like draw a thing and, instead to be good, you do like a little bit and a little bit and a little bit. And then somehow that scratchiness of the drawing starts to give it a little bit more shape. I would say that might be a good analogy here, that the diffusion process is helping you to just a little bit of denoising and then a little bit of denoising. But then when my ear is attached to Wolverine, it's attached better. You know what I mean? So you can look at it that way. So that definitely this is the dominant algorithm right now for generative images. Okay, and if the noise, going from noise to images is hard to swallow right now, just give it time and then you'll accept it. Okay, as that's how it works. All right. Maybe it says something very profound about the universe, right? That we can go from noise to meaning. All right. Anyway, so these are the steps that I mentioned. Basically, we'll cover the rest of the code next week, but it includes these classes. So the Gaussian Fourier projection, it's got a dense layer here. It's got this thing called a unit, right? So you're going to need a neural network for scoring noise levels. You're going to need an autoencoder also for converting an image into the latent representation of it. Okay, so remember, you go from image to a compressed image with some data to the noising process, right? And then there's a few other components. As you can see, it uses conv2D, right? So this is what we saw last week, right? So as I said, I gave an introduction of what convolutions are, but this is a much more complex architecture. You can see it's also much deeper, okay? So this is a ResNet, a res unit. So same idea. Okay, and then basically it's going to have a loss function. Okay, and then this should be the training process. So that you're basically what I recommend in your this week, just start running this code. Make sure that it works. Don't worry that I haven't covered, let's say this unit architecture. I'll take each one of these in the next classes, so I'll cover this next week. You can definitely start reading through it and the code will work, okay? But I need to spend some time in each of these. All right, and then this is the loss function. We'll talk about that as well. There's the Euler-Maruyama sampler thing. The training process. And then basically the prediction. So as you can see, initially it's not going to be very good, right? But it's got some improvements after that you can try. It's got an attention layer, cross attention. And eventually, once you've trained the model, after training, you should be able, as I said, to give it specific inputs, such as the digit that you want, to make it conditional, and it should start rendering the specific number, right? So a 9 or a 1, and you can see these are all 1s. This is a 2, all 2s. This is a 3, and all 3, and so on, okay? So for now, start working on it, okay? And then in the next, so I have a few minutes and I want to show you the blog post so we can start reading through that. And then next week, I will continue describing it, all right? And we're going to continue breaking it down. But because of time constraints, I really wanted to give this to you guys so you can start working on the project right now. Are there any questions of what you need to do for the project? So you use the GPU, you use this code, you need to get your images, decide what your problem is, load them, start training conditionally, right? And start generating something. Okay. And then as we start discussing this in more depth, you can start making at, being creative. The ultimate goal would be to write a little sentence and generate something, but that's difficult. So I can't tell you like use a lot of diversity of images or use images that are very similar. I leave it to you guys to figure out what you want to do. Okay. All right. So that's we have a few minutes. So let me show you the blog post and I'll go over that as well. And then after that, during the second half of today, you guys will do your presentations on your vet GPT, right? So let's go ahead. So here, so latent diffusion. This is I recommend that you guys read this blog post. Okay, so this is the one that I'll be basing. The code is based on this one. And I'll be discussing it. It's pretty good and very detailed with all the aspects. As you can see, this is a very big model, okay? But it talks about all the steps of the process. Okay, and you can see there's these equations, time embedding for neural networks. So there's a lot going on, okay, in this model. Loss function. Attention layers. You can see attention layers are what? The same thing that we looked at with LLMs, right? So it's another application of the attention layer. Generating images, which is the example that I did. So this blog post, the code that I provided on the GitHub is based on this, so you should be able to follow along. All right, so there's a few ideas that I wanted to read off of this blog post that I thought were pretty interesting to describe it. So building a stable diffusion from scratch, right? It's possible for sure. And this is the exact same thing as the GPT that I gave you, right? The exact same thing. You have the code. Same idea as before. The code is not a mystery. In fact, although this seems difficult right now, I'm sure if you guys are driven, you'll read through this blog post, you'll read through the code, we'll have our discussions in lecture, and you will understand it more at the end of the semester, right? Are you going to be masters of this? Do you have to be? Do you know what I mean? You don't always have to master everything, right? So think about how this works, how you should approach something like this, right? Read the stuff, break it into parts, kind of understand the concepts, the things that are important that aren't important, right? But with the GPT also, right? You saw there was a lot there. This one has a lot. So although you have the code, can you basically go and create your own OpenAI right now with this code? No. Same problem. What are the limitations? GPU. How many GPUs do you currently have? One, right? At best. I couldn't even get one right now for the class, right? So you're limited once again. How many would you need? So many. Elon Musk is building a cluster right now with 100,000 GPUs. So is Facebook. How can we ever compete with them, right? But anyway, so that's the limitation is the computing power. Also, that they have all the images in the world. Meta has an advantage there, right? They have all the pictures. And this is a picture-driven problem. So whereas with guys? So if you think about it, you know, that last homework was you collected some text. Text is not as big as images, right? So now you're moving into the realm of images. Also, MNIST is black and white. But to make your project more interesting, use color images. Do you guys see that? Color images are 3 times as big, right? Which means you're going to need more computing power. Got it? So anyway, it's the same idea as before, even though we can understand the code, and that's not the secret. You know, we're still limited by computing power and images. So building a stable diffusion from scratch is possible, which you can see in this blog. But achieving the current quality found in the market, similar to Stability AI, that they built, is challenging due to the substantial amount of data and computation required. All right, so that's one of the key things, like, to understand, right? That the limitation of building things from scratch. But it's good, though, to understand things, because I'm pretty sure, you know, once you start using transfer learning, you'll just understand better what you're doing, right? You want to take out the mystery out of things, okay? That's the whole point. Hopefully by now, that if you go and fine tune a llama, right, you've done a GPT. So you've taken some mystery out of it, right? You have some understanding of how it works, okay? So anyway, that's, so the same idea applies with this one. Yeah, so scaling it to 1 billion parameters as done by the other companies demands the same powerful computation and extensive data resources. So you guys can read through this one. You know, this blog post will just show how to do this with MNIST. Let's just look at the table of contents here to see everything that's involved in this model. So how does stable diffusion works? It's got, you know, the architecture of stable diffusion, obviously dealing with the data set. There's a basic forward diffusion, right? Create a basic forward diffusion, creating a basic reverse diffusion. That was the topic of today. I did a simplified version of that just to kind of illustrate the idea of noise, okay? All right, there's going to be a learning score function. This is interesting because this is also used in LLMs, right? In LLMs, you have this thing called a reward function, which basically you have a question and an answer, and the reward function looks at both of them and says, that's good versus that's bad. Humans can look at something and say, oh yeah, this is a good answer given the question, right? But how do you train a neural network how to do that, right? So you have to probably build a neural network with those examples so that when you give it a new pair of question and answer, it provides a score. Here we have the idea of a score as well, but for noise, okay? So we have that for noise. So then other parts of the stable diffusion model are a time embedding for the neural network. So think about that, right? So we learn about embeddings, which are vectors out of something. Here we just have to embed the time component as well, okay? So that's part of it. You're going to have a unit, which a unit is just a neural network, okay? So it's sometimes you have neural networks that have many layers of convolutions and things like that, and they get specific names based on what they do. So in this case, it says we're using a unit, so it's a specific type of a CNN. All right, so next lecture, that's one of the topics that I'm going to address, more just what units are, okay? But for now, this is what we're doing. So if you've taken other classes, maybe you've heard of a ResNet, right? Or a VGG, right? So these are all types of architectures that have been studied, and eventually they arrived at a specific configuration. All right, so coding a unit architecture with concatenation, coding a unit architecture with addition. So the forward diffusion process with exponential noise, the loss function, of course, so there's going to be a specific loss function for this process, and we're going to discuss that a little later as well. Building attention layers, all right, so how can that be added? Coding a unit architecture with spatial transformer, updating a unit loss with denoising conditions, and so on. So as you can see, there's basically, these are the elements that need to be addressed, okay? Same as before, so it's OP, PyTorch, you need to understand the concepts of tensor operations. All right, so how does stable diffusion work, right? So we have a few minutes, so let's kind of go over this. So stable diffusion operates differently compared to many other image generation models. In simple terms, diffusion models use fuzzy noise to encode an image, okay? They then use a noise predictor along with a reverse diffusion process to put the image back together. Do you guys see that? So that's like the trick of it, right? So diffusion models use fuzzy noise to encode an image, right? So you take the image, you noise it, you arrive at the noise image. Then they use a noise predictor, which is that neural network, that score one that you saw in the example, right? Along with the reverse process, diffusion process, and you put the image back together, okay? Stable diffusion stands out by not using the pixel space of the image, right? Instead, it uses a simplified latent space. So we've talked about this term, right? Latent, right? We did this actually in a previous example with text, if you remember. We converted to this singular value decomposition, if you remember, right? We took the text and then we did the clustering approach. So it's the same idea here. So you take the original images, you kind of shrink them into a smaller grid, that's still it's like an image, but it's like there's a neural network that will take the original image and produce the latent image. And how do you do that? You use an encoder, right? So that means we have to talk about encoders and decoders, right? Or something called the autoencoder, right? So if you've ever heard of that, right? So that's, something also that we need to address a little bit. So we'll do that in the next class. All right, so as I said, stable diffusion stands out by not using the pixel space in the image. Instead, it uses a simplified latent space. This choice is driven by the fact that a color image with 512 by 512 resolution has a huge number of potential values. In comparison, stable diffusion uses a compressed image that is 48 times smaller, right? So obviously, the reason is for the impact in GPU power. So containing fewer values. This significant reduction in processing requirements allows the use of stable diffusion on a desktop computer with an NVIDIA GPU featuring 8 GB of RAM. Now, this is kind of like the intuition. So the effectiveness of the smaller latent space is based on the idea that natural images follow patterns rather than randomness. So it's saying you have an original image, but do you really need all that information, right? Let's compress it and let's have the neural network, right, know how to compress it. So that's the key insight. And how does that work? With the weights, right? So think of it like this. You have the image. It goes through a neural network to a latent representation. If that's bad, during training, we're going to see that. So what do? You use the back propagation, right, to tell it to try different weights, right? So then next time it gets the original image with a new set of weights, a new latent representation, and maybe that one's going to be better, right? So it's the same process as before. Let the neural network figure out how to compress from this image to the latent image until we have a good representation, right? And capture these patterns. So stable diffusion uses what is called a variational autoencoder, VAE, in the decoder to capture intricate details, such as eyes and so on. So that's basically one component of this architecture, right? So we're going to need to compress the data, and that's going to be reflected in the neural network. So if we look back at the example that I had, So if we look back at the example, you'll see that we have encoding and encoder and decoder layers. We go to the unit. See encoding layers, you can see that there, and where the resolution decreases. And so that's the idea, right? So we start with the image, but the neural network will need to learn how to do that compression, right? So, and that's done through convolutional layers. All right, so yeah. All right, so anyway, so this is kind of the idea. So a cat taking a selfie, so it goes through Stable Diffusion and it produces a cat, taking a selfie. So the idea being that this process of Stable Diffusion will achieve the best results. So I'll kind of wrap up with this one, and then we'll take a 10-minute break and start doing the vet presentations. So the key takeaway from today, guys, is the final term project has been assigned, right? Form your groups of 3. This is your code. Start working on it. The first thing you should do, replicate what I have there, okay? Generate MNIST digits. After that, once you've replicated and you know that it works, start thinking of the problem, the data set, start looking at the code, and as we continue our discussions, maybe you'll figure out modifications and things like that, okay? Any questions about that? Should be a fun project. Okay, I think it should be fun to generate images and so on. All right, so the architecture of Stable Diffusion, Stable Diffusion uses several main architectural components. So what are they? A variational autoencoder. So this is one of the reasons why I like this example, because it allows me to touch on many topics of deep learning in a way that you see them kind of interact together, right? So some people just use variational autoencoders for their problem and nothing else, all right? So, variational autoencoder consists of an encoder and a decoder. The encoder compresses a 512 by 512 pixel image into a smaller 64 by 64 model in latent space, right? The representation. The decoder restores the model from the latent space into the full 512 by 512 image. So actually, that part can be understood just as an autoencoder and then added to Stable Diffusion. You see what I'm saying? So it's like a thing made out of many smaller things. The forward diffusion adds Gaussian noise to an image progressively until only random noise remains, like the example I gave you. Used during training, but not for other tasks. Make sense? Goes back to your question, right? So we don't care about noising things, but it's used during training. We do care about the reverse part, though. And that's the part that we're going to take out and use for our applications. So it's used during training, but not for other tasks, except, image-to-image conversion. The reverse diffusion iteratively undoes the forward diffusion, trained on billions of images using prompts to create unique images. So this is the key, right? Trained on billions of images using prompts to create unique images. So of course, you can't do that for your project, but you will train it on thousands of images. And instead of prompts, I've given you an example of just giving it like a vector of a 1 or a 2. What is this, think of this idea, right? That 1, 2, or 3 that we gave it, what is it really? Do we ever give neural networks a 1, a 3, a 7? No. What do we usually give them? A vector. We give it a vector, right? Everything is a vector, right? Text is a vector. This number is a vector. So if I have 10 numbers, what's a sufficient vector that I can use in size? Like what kind of a vector can I use? a vector of size 10 should be sufficient as input, right? Because a one hot encoded vector of size 10 is enough to provide if it's a 1, if it's a 3, if it's a 7, right? Now, we can take a sentence and embed it into something that is of size 1000 maybe, or a word, right? So we've seen this many times already where we take some input and embed it into a vector, right? So that's basically the idea. So these prompts are just embedding. So you can think of it as the 7 or something more complex, okay? All right, so the reverse diffusion iteratively undoes the forward diffusion, trained on billions of images using prompts to create unique images. The noise predictor, based on a unit, utilizes a unit model for denoising images. The unit models are convolutional neural networks with stable diffusion using a residual neural network. So this actually brings up resonance, right? So that's what is a resonant? Basically, remember last week we did a CNN of 2 layers? A resonant is kind of the same thing, but just very deep. Okay, that's all, and with some additional components, but it's essentially the same thing. Got it? Okay. All right, so you will learn a little bit about what a resonant looks like when we do this. The text conditioning. So obviously in this example, there's no text being used. That is hopefully what you will do for your term project, okay? So try to add at least keywords or something like that. So the text conditioning, text prompts are a common form of conditioning. What the conditioning means is, in this example, when I said 7, it rendered images of a 7. 3, images of a 3. So conditioning means that. And it's very simple in its simplest form. Noise, and you concatenate the 3 or the 7 or the 5 to it. Do you see what I'm saying? So you have a vector of whatever the input is, and then you can concatenate to it another vector which has your condition, okay, in its simplest form. So text prompts are a common form of conditioning. A clip tokenizer analyzes each word in a textual prompt and embeds the data into a 768 value vector. So there is this thing called clip. It's a type of a neural network that basically can help you to go from text to embeddings, right? So this is a solution that you can consider. Up to 75 tokens can be used in a prompt. Okay, so that's actually very good. And then text prompts are fed from the text encoder to the unit noise predictor using a text transformer. Okay, so this piece is a little bit more complex. There's quite a bit going on there, and so on. So anyway, so I think we're a little bit over time. Please start reading through this blog. We'll continue to cover some of these ideas in the next 2 weeks, okay? And replicate this code and start working on your term project, okay? Any questions? Are you excited or terrified? All right, so mostly terrified. All right, great. All right, well, as I said, the first thing is just replicate this example, all right? And hopefully then, and then the next step would be to add your own images, okay? And we'll go from there. All right, so I'm gonna start the recording here. And we need to